Okay. Hello everyone. Hello Professor. Group 4 and our team name is EcoHoop. Our project Energy Aware Hoop Count Routing in a 12 node chain wireless sensor network, and we'll talk briefly explain why what is the scenario matters and how it designed to network in the OMNet plus and the matrix we collected and what we observe about the reliability and delay and energy. So why this scenario matters? The wireless sensor network typically runs on the batteries and are often deployed in the places where the changing the batteries is difficult. And that means the routing decision directly affects how long the network can operate as well the delay and reliability of the data. The simple hoop counts routing in the easy, but it trends to overseas the nodes needs to sync and the count the short the lifetime, and our group 4 scenario focus on the 12 node chains with the bursty traffic and the energy aware hoop count scheme to see how well it behaves. So the overview, we summarize the setup. The topology is linear chain of the 12 nodes with the node 0 acting as the source and the node 11 as the sink. So the traffic flows from the source towards the sink in the burst, and we compare two behavior, a baseline hoop count protocol and the energy aware hoop count variant. Our main measurements are end-to-end delay, packets, delivery ratio, and residual energy. So we can understand basic energy reliability trades off in the WSN. So our main introduction and the motivation is the wireless sensor nodes operates on the limited batteries and hard to repair once deployed. Because of that, routing is not just about the finding a path, it's a strong effect network lifeline and latency and reliability. The pure hoop counts routing is the widely because it's simple but it can overload nodes close to the sink. Our idea is to keep the hoop count structured but and the lightweight every energy aware twist and see how it behaves in a control chain scenario. So the next slide is gonna explain by my friend.
Each node is a compound module composed of several submodules. Node core handles routing logic but burst generation at the source, energy accounting, and statistics. Radio stores radio parameters such as transmission range. App controls traffic type, packet interval, and payload size. Energy tracks battery level using TX, RX, and sleep currents, and routing configuration holds the protocol names and the flag that enables alternating baseline versus AHC along the chain. And in the next slide, which is routing behaviors, traffic model, and energy. For the routing, the baseline protocol strictly follows hop count. If the node index is less than the destination, it it forwards right, otherwise it forwards left. The energy aware hop count uses the same rule, but if residual energy drops below a threshold and the node has two neighbors, it may randomize the next hop to avoid overusing one side. Only node 0 generates traffic using a bursty patterns. Burst repeats roughly every 8 hours with packets inside a burst spaced about zero point 0.2 seconds apart and a payload of 64 bytes. So each energy packet is computed from current, voltage, and event duration. Each node continuously updates its remaining energy, and the next slides will be explained by my friend.
Coming to the next slides, design and configuration of topology and nodes. This slide shows the remaining energy of each node. Nodes near the sink use more energy because they forward more packets. EAHC and the baseline look similar here since the run is only 30 minutes, but the over longer run we would see bigger difference. Coming to the next slide, the methodology. This slide shows the packet delivery ratio for each node. All the nodes have very higher PDR, meaning they forward packets reliably. Even with the bursty traffic, the chain remains stable and doesn't drop many packets. Coming to the next slide, the continuation of the methodology. After the simulations, we process the scalar result offline. We use We use OPS KV tool to export the scalar values from the .sac file to CSV. A Python scripts with pandas and the MATLAB convert those scalars into per node metric tables, computes packet delivery ratios, and generates the plots. This pipeline gives us four main figures: residual energy per node PDR, the network wide PDR, and the average delays at the end of the sync for the different runs. The next slides will be explained by another friend.
Okay, coming to the results, this slide shows figure 1, which is final residual energy per node for one representative run. You can see that all nodes retain most of their initial energy after 30 minutes. Nodes close to the source and sink consume slightly more energy because they handle more traffic, but overall the energy distribution is still very uniform. This tells us that for the current traffic level and the simulation length, the network is far from battery depletion. And coming to the next slide, which is per node PDR. Here we focus on reliability and delay. The per node PDR is close to 1 for the relay nodes, meaning almost every packet that should be forwarded actually is there. At the network level, the PDF from source to sink is effectively 1. So we see almost no packet loss. And coming to average end-to-end delay at the sink is also extremely small, which is expected because our MAC by PHY model is simple and there is no heavy contention in this chain. And coming to the next slide, which is network wide PDR. In this section, which explains the network wide packet delivery ratio or PDR, which measures overall reliability of a WSN. In our simulation, the source generated 1350 packets and the sink successfully received all packets. This gives us PDR of 1, meaning the network delivered every packet without loss. This indicates excellent reliability and confirms that our routing protocol performed very effectively under the tested conditions. And next slide will be continued by my friend. Thank you.
So coming to the results, like the end-to-end delay, the previous slide, please. So in the results, the average end-to-end delay at the sync is effectively zeros in the abstraction. So paths are short at most like 11 hops, and there is no explicit interference or contention. So packets travel without noticeable queuing, all three runs showing nearly identical delay values. So coming to this particular slide, the discussions, putting these all results together, the chain WSN behaves as a highly reliable path under the group 4 configuration. So we get near perfect delivery and almost zero delay with only mild energy imbalance between nodes. The energy-aware hop count logic is in place, but in a 30-minute window with moderate traffic, the low energy condition is rarely triggered, so its effect is subtle. We expect each to show a stronger benefit if we extend the runtime and increase the traffic and more complex topologies and interference. So the limitations are simply MAC and one topology as no details relate counters. So coming to the conclusion, to conclude our project, we built an evaluated and energy-aware hop counting routing scheme in a 12-node chain WSN using Omnet++ and the Python analysis pipeline. Under this assigned group 4 scenario, the network achieves near perfect PDR, a very low delay, and a fairly balanced energy profiles across nodes. This shows that our implementation satisfies the project requirements for topology modeling, protocol behavior, and the metrics analysis. So in the future, we would like to stress the network with longer runs and more demanding traffic to better highlight the benefits of the energy aware of like routing scheme. Thank you, and we are happy to take any questions you have.